Friends, this video we are going to see inner product and inner product space, then few examples. First we start with the definition of inner product. An inner product on a vector space V is a function that to each pair of vectors so namely we can say u and v. U is a vector and v is a vector. This is a vector, this is also a vector u and v associated a real number. So we use that is u comma v is a and satisfies the following axioms. For all u, v, w in vector space V and all scalars C. So what is the first condition? Symmetric. That is, so this is the notation for inner product u comma v equal to v comma u. Because I am using, it's associated with the real number. That is why it's condition. It's a complex number, it's just a different case. So we see only the real inner product space only. Second condition is u plus v comma w equal to u comma w plus v comma w. So linear about the first component. Third one is homogeneity. C times u, because C is a scalar, u is a vector, comma w equal to C times inner product of u comma w. And fourth condition is positive definite. U comma u is always greater than or equal to 0 and the equality holds, that is u comma u equal to 0 implies u must be a 0 vector. So this four condition we call it as, then we say that a inner product. Now we say what is the inner product space? A vector space V with an inner product is called an inner product space. Okay. So the inner product space means first we need the inner product. This inner product means it satisfies these four conditions. First is symmetric, second is the linear about the first component, and this is a homogeneity condition. Fourth is a positive definiteness. Yes. Now we see few example. First we start with the some Rn. Example. Suppose my vector space V equal to Rn. So I define U V, see vector in V, that is in Rn. So what is a U vector? I can write it as U1, U2 and so on, Un, because so I use a column vector. V also V1, V2 and so on, Vn. So inner product of U comma V equal to U transpose times V. That is a matrix multiplication you can do. That is U1 times V1 plus U2 times V2 and so on, Un times Vn. So this is the inner product. So what is the first condition? That is, first condition is we have to check this is the inner product or not. First condition, condition 1 is U comma V equal to V comma U. So what is the meaning will come? We want to prove this condition. So first I will take left hand side. U comma V equal to U1, V1, U2, V2 and so on, Un, Vn. So I know that this is some scalars only, U1, V1. So you can represent V1 and U1 also same. So I can represent V1 times U1 plus V2 times U2 and so on, Vn times Un. So next step you can represent directly. This is equal to V vector transpose times U vector. This is nothing but V comma U. So symmetric is satisfied. So our first condition is valid. What about the second condition? Second condition is U plus V comma W equal to U comma W plus V comma. What will come? This first we take the left hand side, that is U plus V comma W. What will come? This is one is U1 plus V1 comma W. So it's multiplied with W1 plus U2 plus V2 times W2 and so on, Un plus Vn times Wn you can write. The next step you can write that U1 W1 V1 W1 plus U2 W2 plus V2 W2 and so on, Un Wn plus Vn Wn. You can write. So then you can separately Un terms and Vn terms. That is U1 W1 plus U2 W2 and so on. Un Wn. This is the first term, and plus V1 W1 plus V2 W2 and so on. Vn Wn we can separate. So the first term will come here like that will come, this terms is coming here. So this is nothing but our inner product of U comma W plus this one is V comma W, inner product of V comma W. So our second condition is satisfied. What about third condition? Third condition is quite obvious. That is some scalar C times U comma V. Yes, we can write it as, so we want to prove that C times inner product of U comma V. So what is C times U means? So now you take the left hand side, inner product of Cu comma V equal to C times U1 V1 plus C times U2 times V2 and so on. Cn times Un Vn. You can write. Then you take commonly out, taken out the U. So you take as U1 V1 U2 V2 and so on. Un Vn. So now you take it, this is nothing but this is C times inner product of U comma V. So third condition also satisfies. Now what is the fourth condition? Positive definiteness. U comma U is always greater than or equal to 0. So this implies you take it as, what is the U comma U? U comma U is U1 square plus U2 square and so on. Un square. So these all are the positive numbers, non-negative numbers basically. So it's always, if you have sum of all non-negative numbers, it gives non-negative. So that can say, suppose this becomes 0, it's only possible all the entries are 0. That is U1 is 0, that is U1 square is 0 and U2 square is 0 and Un square is 0. It's possible only U1, U2, all components are 0. So this implies if U comma U equal to 0, if and only if U is a 0 vector. So this is the first condition. So this type of inner part we call it as we already basically we studied in our school classes. So it is type of, this is inner product. This type of inner product we call as a dot product. We already studied, correct, in our vector algebra class. Dot product. Now some other example, another simple example we take the same way. Suppose now I take example, another example. Suppose I take V equal to R2. So very simple example I take. Now I define U comma V belongs to R2. Then I define the inner part is U comma V is 4 times E1 V1 plus 5 times U2 times V2. Okay. So I define the inner part such a way. Now it satisfies these conditions. Quite obvious. Here look, the same way only we are going to consider. Here only the 4 condition will be coming. So it does not affect our inner first 2 conditions. So we want to worry about the 4th condition. Okay. So whenever this number of numbers will come, we only worry about the 4th condition only. Because other 3 conditions are very quite obvious will come. Anyhow, we start with the first axiom. Axiom, what is the first condition is? U comma V equal to V comma U. This is my first axiom. So now I take as usual left hand side U comma V equal to 4 times U1 V1 plus 5 times U2 V2. Now you can write it 4 times V1 times U1 plus 5 times V2 times U2. Because these two are the scalars, like our previous case how we can do it similarly. Now this can be, I can write as V comma U. So the first condition is automatically it satisfies. What is this? Now we go for the second axiom, that is U plus V comma W equal to U comma W plus V comma W. So now I take the left hand side U plus V comma W. This is, I can write as 4 times U1 plus V1 times W1 plus 5 times U2 plus V2 times W2. So this is nothing but 4 times U1 W1 plus 4 times V1 W1 plus 5 times U2 W2 5 times V2 times W2. So you can take directly 4 times U1 W1. So another term, this one is plus 5 times U2 W2. So now I segregate what is the U term separately and V term separately. Plus 4 times V1 W1 plus 5 times V2 W2. So this is nothing but this is inner part of U comma W. This is V comma W. So this is my second axiom is satisfied. What about the third axiom? So homogeneity condition. So C of U is simply we write it 4 times C times U1 times W1 plus 5 times C times U2 W2. So now this is, you commonly take the C outside. This is 4 times U1 W1 plus 5 times U2. So now you take it, this is C times inner part of U comma W. So the homogeneity condition is true. The finally non-active positive definite, that is U comma U is 4 times U1 square plus 5 times U2 square. These all are non-negative, must be positive. So same argument in the previous example. Now we see another example. So last two examples are defined on the Euclidean space. Now we are going for the non-Euclidean space. Example 3. Let V equal to set of all continuous function defined on 0, 1 be a vector space. We already know that. Of real valued I am taking. Continuous function on 0, 1 for any two functions f of x and g of x in V. We define inner part as inner part of f comma g is integral over 0 to 1 f of x times g of x dx. So to prove that we require advanced calculus. Okay, anyhow I will try to prove from little point of view. Okay, so in the layman point of view also I can prove very simple manner. The first few conditions are very easy to prove, but to prove that you require advanced calculus is required. That's only I want to say. First axiom is inner part of f comma g equal to g comma f. The symmetry, that is very obvious case here. Inner part of f comma g, I take left hand side, then integral over 0 to 1 f of x times g of x dx. So I can write it as integral 0 to 1, this is g of x times f of x dx. So this is nothing but inner part of g comma f. What about the second condition? Second condition is like inner part of f plus g comma h equal to, we have to prove f comma h plus g comma h. So this is, so now I take left hand side, f of plus g comma h is integral over 0 to 1 f plus g times h. These are the functions f of x, g of x. So now you can multiply inside f of x times h of x plus g of x times h of x times dx. So now you can separately you can write it as f of x using the integration property you can write. So this is nothing but inner part of f comma h plus g comma h. This one only I want to prove that. So second axiom also true. Now we go for the third axiom, that is homogeneity axiom. C times F comma G equal to C times inner product of F comma G. So as usual, I take the different sign. C times F comma G equal to inner product of 0 to 1 C times F of X G of X dx. Correct? Now you look, this is some constant. You can, because my integral operation is always linear, so I take the outside C, 0 to 1 F of X times G of X dx. So this is nothing but C times inner product of F comma G. The fourth conditions only very difficult to prove in the elementary level. So that is inner product of F comma F is always greater than or equal to 0. That's I want to prove. Okay, so what is F comma F? So integral over 0 to 1 F square of X dx. So F square of is always a positive non-negative function. So this is always greater than 0. So only possible 0 whenever F is 0. So this condition to prove that the advanced calculus is required. You won't see any advanced calculus. This theorem is already proven. That is, F is a continuous function. F is continuous. F is non-negative. This implies integral over a to b F of X dx is also non-negative. This theorem is available in all the advanced calculus book. Please check it. So using that fact, we can prove that this is always non-negative. I hope in this video what is the inner product and how to check if this is inner product or not, and what is the inner product space also. Thank you for watching this video.